So 1 second. Okay, here we are. So we start by being able to define a curve in 3 dimensions. So we already talked about lines, and we said that you can define a line, you can define a curve R of t to be equal to R0 plus TV. Let me see. If I can close some windows to make that go a little faster. Okay. So this was a line in R3, and we said that if here are your axis x, y, and z, okay, then our line over here, it starts at R0, so it starts at R0, and then you have a line, and maybe it looks something like this, and the vector v lies on this line. So here's the vector v, and so that's my R of t. Now in general, we can have an R of t which is equal to x of t. I'm not sure why this is taking so slowly. Okay, which is equal to x of t, y of t, and z of t. Yeah. And so this over here is going to also define a curve in 3 dimensions. Let me see if I can kind of restart this. But anyway, regardless, so going back here, we have our R of t, which is equal to x of t, y of t, z of t. And in this situation, we are talking about a curve in R3. So maybe over here we're at T1, here we're at T2, T3, and we continue going like that. Okay. So examples for this can be R of t is equal to t squared. So here my x of t, and this is what the x coordinate is doing. That's equal to t squared. My y of t is equal to e to the t, and my z of t is equal to 4 minus 7t. And again here, they're telling us that we already saw what a line is. So a line is R0 plus TV, which is going to get you to that. Okay. So now they ask us to find the curve R of t is equal to cosine of t, sine of t, and 1. So we have R of t is equal to cosine of t, sine of t, and 1. So that tells us that x of t is equal to cosine of t, and y of t is equal to sine of t. Tells us that x of t squared plus y of t squared is going to be equal to 1, because this over here is cosine of t squared plus, and this over here is sine of t squared. So that is equal to 1. So this over here is equal to 1. So that tells us that those two things are equal to 1. So in general, the sine is just going to be 1. So I'm going to be at 1 in sine. And then in the xy coordinate, you see if I take my x and my y and I square them, I get 1. And this over here is the equation of a circle. This tells me, oh, if I take my x and a y coordinate, I square the 2, I get 1. So that would give me a circle. So I'm going to get a circle with radius 1, 1 unit high, and then you just have a circle. And this over here is from the fact that we have cosine of t and sine of t in my x and y coordinates. And then the 1 gives me my height. Any questions about this? Is it clear?
It is.
Okay, perfect. So, yeah. Now, and they also ask us, what's the difference between this curve, the circle, and the path, r of t? And the main difference is that r of t is in terms of t. So as t changes, maybe this is t1, t2, t3, and then I can come back, t4, and then maybe I'm back here, now I'm t5. So I'm going around this thing. The curve is just a circle, so they are different. Okay, now they're asking us to describe the curve traced by negative sine of t, cosine of t, and t for t positive in terms of the projection onto the coordinate planes. So now we have r of t is equal to negative sine of t, cosine of t, and t. So in the z plane, so let's forget about the projections just for a second and try to understand what this does in general. In the z plane, it just goes up. So the t is increasing. So as and if you were to project this onto the z plane, so let's say you would remove the y-axis. Okay, I don't want to look at that at the moment. So one second. So yeah, so the t just increases, and so now I have that x of t is equal to negative sine of t, y of t is equal to cosine of t, and same thing as before, we have that x of t squared plus y of t squared is equal to 1. Same thing as before. So you get a circle, and then the t increases. So you actually get up, you end up having a helix. Okay, maybe not perfect. And because that t can only be positive, it does not have a negative part. So again, you have circles. So from here to here, you can imagine a circle of unit 1. If I just collapse this, and similarly from here to here. But they are increasing because of this t, so they are increasing. With regards to projecting these onto different planes, so let's first try the xz plane. So the xz plane, so this happens when y is equal to 0. So we get negative sine of t, 0, and t. So now we can imagine a situation where my z is over here and my x is over here. So here's my t, here's my x, and if I have negative sine of t, I would be doing something like this. So that would be the projection onto the x z coordinate system, and again you would get something. Well, I'm not going to draw it here, but it would be projected onto here. You would have your x, your z, so you can just put that down, lie it down, and then you're going to have a zigzag over here. You're going to have some type of zigzag. And the same thing would be true between cosine and t. You'd be getting a zigzag in the zy direction. So let's say you had zy, and you would be getting something like this. Okay. And because it's cosine. And then if you project it onto, so this is in the ZY plane. Okay, and then if you project it onto the XY plane, so XY plane, that tells me that Z is equal to 0. So I have negative sine of t, cosine of t, and 0. So now we're projecting down to the XY plane. And over here, again, if I take this to be my x of t and this to be my y of t, x squared plus y squared is equal to 1. So I have a curve. And that's kind of like taking this picture and pressing it down onto the XY plane, and you will get a circle like that. Any questions about this? So yeah, so these are the pictures that you get. You get your spiral, you get a projection into the XZ direction that looks like sine, projection into the YZ direction that looks like cosine, and a projection into the XY plane that is a circle. Okay, so now they're asking us, they give us two surfaces. And one of the surfaces is this surface over here, which is your saddle. And another surface is your cylinder, x squared plus y squared is equal to 4. And they ask us, they tell us, well, okay, a curve results from this. Here's my curve. And they ask us to parameterize it for y bigger or equal to 0. Okay, so the equation of the surface is x squared minus y squared is equal to z minus 1. X squared minus y squared is equal to z minus 1. And then we also have x squared plus y squared is equal to 1. Okay, so now we want to fill out the curve. So we have r of t equal to x of t. So we want to find our x of t, our y in terms of t, and our z in terms of t. So we can say, okay, let's just take our x to be t. So that takes us x is equal to t. We won't change anything yet, but let's now solve for y in terms of x. So from here, we're going to get that y squared is equal to 1 minus x squared, which tells us that y is equal to the square root of 1 minus x squared. And now if x is equal to t, in this component, I can just put in 1 minus t squared. So that's the y component. And because that y, we want y to be bigger or equal to 0. So because that's the case, over here, we can only have t between, so 1 less than or equal to t less than or equal to 1, because we're squaring it. Okay, now negative 1. Okay, and then for the last part, we take our y and we plug it into our y over here. So that's going to give us x squared minus, and then the square root and the square cancel, so we get 1 minus x squared. That's this is equal to z minus 1. So that tells us that z is going to be equal to x squared minus minus is plus, so 2x squared. And then we add a 1. Okay, let me just make sure. There's a So I wrote this down. Okay, there's a 4 here. So okay. Let's redo some of this. So here there should be a 4, and here there should be a 4. Means here there's a 4. Here's a 4. So that means that this over here is 2. Here's a 4. Okay. Okay. So now this is going to be 2x squared minus 1 plus 1, so plus minus 3. Okay. Okay. So again, so now my R of t is going to be equal to t to the square root of 4 minus t squared and to 2t squared minus 3. And now my t is going to be bigger or equal to -2 and less than or equal to 2. And this is going to be my curve. So this is the curve that we were looking for. It looks something like this. So it's this curve over here. So it's this curve over here. Any questions about that? Is this clear?
Yeah, it's clear.
Okay. So now they want us to parameterize the circle with radius 3 centered at 2, 6, 8. And they want us to parameterize it with the xy plane parallel to the xy plane and parallel to the xz plane. Okay, so what we can do is we can first look at the center of this circle, and that's going to be the point at 268. So this is the point 268. And then we need to add a circle over here. So first we need a vector that goes to 268. So our R of t is going to be equal to the vector 2, 6, 8. So now we're in the center of this circle. So we're going to add to that a circle. And if we want it to be parallel to the xy plane, that's what they asked, xy plane. Then, so first, in order to find a circle, so let's just go for a second to the xy plane. So here we're in the xy plane. Let's say you wanted to find a circle of radius 3 over here. So if you look at 3 cosine of t and 3 sine of t, in the xy plane, and now if you square them, so x of t squared plus y of t squared, well, now that's equal to 9. So this would be a circle with radius 3. Okay, so here's my radius, that's radius 3. So now this is going to be this plus, and then I'm going to have 3 cosine of t, 3 sine of t, and 0, because in the z plane it's 0. So that's how I would make the circle in R2 parallel to the xy plane. Yeah, and that's that 2, 6, 8 plus, and then you have your x and your y. Now, if you want to make this parallel to the xz plane, all you really have to do is you have to set your y to be equal to 0. So in the xz plane, you would get R2 of t is equal to 268 plus 3 cosine of t, 0, 3 sine of t. Okay. And here are how your two circles look. Any questions about this? Okay. So in summary, we are looking at R of t, which is an equation with 3 different components, and it creates a curve in space. Okay. So now what we're going to do is we're going to take a lot of the things that we did in Calc 1 and we're going to apply it to 3 dimensions. So the first thing that we should know is that limits in this case exist. So there's such a thing as the limit one second. Yeah. As t goes to t0 of R of t. So we can take this limit, and this is going to be equal to, and you just go into every component. And limit as t goes to t0 of z of t. Okay, so yeah, limits exist. You just go into each component individually. So the limit of this would be the limit of this plus, and the limit of that and this component, and so on. So here they give us an easy example. Calculate R of t for t going to 3 of this thing. So now my R of t is equal to t squared, 1 minus t, and t to the negative 1. So the limit as t goes to 3 of R of t, if I put it in every component, they're all continuous at t. So this is going to be 9, plugging it in, negative 2, and 1 over 3. Okay. And we can also look at the derivative. So R prime of t is going to be the limit as h goes to 0 of R of t plus h minus R of t over h. This going into every component would just be the limit as t goes to 0 of x of t plus h minus x of t over h lim t as h goes to 0 of y of t plus h minus y of t over h, and then limit as t goes to 0 of z of t plus h minus z of t over h. And now notice that this thing is equal to x prime of t, y prime of t, z prime of t. So that tells us that R prime of t is equal to x prime of t, y prime of t, and z prime of t. So that's this over here. The derivative is the derivative of each component. So if we're looking at t squared 3t and sine of t as my r of t, and its derivative is going to be 2t 3t squared and cosine of t. And same thing here. The derivative of cosine of t is negative sine of t. The derivative of negative 1 is 0. The derivative of e to the 2t is 2e to the 2t. So we're just taking the derivative of each component individually. And we can take second derivatives, third derivatives, so forth. So they're asking us to calculate the second derivative of this r of t. So r of t is equal to ln of t, t and t squared. So r prime of t is going to be equal to 1 over t, 1 and 2t. And so then r double prime of t is going to be equal to negative 1 over t squared, 0 and 2. And they want us to calculate it at 3, so r double prime at 3 is going to be negative 1 over 9, 0 and 2. Any questions about this? So again, we have to remember the rule for addition, the rule for constants going to come out, and the product rule. So the derivative of f of t, r of t, f is a scalar valued function, so it can be multiplied in as a scalar, is the derivative of f prime r of t and f of t r prime of t. And we should also remember the chain rule. So all the rules for differentiation hold here too. There really is no reason why they shouldn't. It goes into each component. The only one that they're proving here is the second one, which makes sense. It's the only really new property. So if r of t, let's call this h of t, is equal to f of t, r of t. Now r of t is a vector and f of t is a constant function. Then h prime of t is going to be, well, it's the same as f of t x of t f of t y of t and f of t z of t. And so now the derivative, we're going to do the product rule for each one of these. So that's going to give us f of t x prime of t plus f prime of t x of t, so on and so forth. And so then this is going to be equal to f of t r prime of t plus r of t f prime of t, which is what we wanted. Any questions about this? Okay. So now they want us to try an example. So let R of t equal to this and f of t equal to this. They want us to calculate these two things. So the first one, we would have, well, we can just calculate what R prime of t is. That's going to be 2t, 5, and 0. And what is f prime of t? F prime of t is going to be equal to 3e to the 3t. So then d over dt of f of t, R of t, is equal to R of prime times f of t, so that's this, 2t, 5, 0, times my f of t, which is 3 e to the 3t, plus f prime of t, so 3e to the 3t, times r of t, which is 2 t squared, 5t, and 1. So that over here is, oh, and that's what they get. Okay, so this over here, 2t, 5, and 0 is this, and this over here is this. All right. Now for the second part, we just need the chain rule. So d over dt of r of f of t. Okay, this is going to be equal to r prime of f of t times f prime of t, which is going to be equal to 2 to the e 3t okay, and then 5 and 0 times 3e to the 3t. Okay, so that's that. Okay, any questions about this? Okay, the dot product and the cross product both have similar rules. So again, this is R1 prime dotted with R2, R1, R2 prime, and this is R1 prime cross with R2 plus R2 cross, R1 cross with R2 prime. So the same thing happens here. And for the cross product, you can go to the 3 components individually and make sure that that's correct. Okay. So now they want us to prove that R of t cross R prime of t is equal to R of t cross R double prime of t. So d over dt of R of t cross R prime of t, R of t cross R prime of t. Okay. Good. So now this over here is going to be equal to this times the derivative of that. So R of t cross R double prime of t plus this cross R prime of t. But these are going to be going in the same direction, same vector, so their cross product is 0. So then this gives us R of t cross R double prime of t. Which is probably what they wanted. R of t, R double prime of t. Perfect. Okay, good. Now, like with Calc 1, the derivative plays the role of a tangent line. So if we are in x, y, z, if we have a curve, then our derivative at this point, so you can take a look at r prime of t, will give you a vector, and that vector is tangent to this line. Okay. So that's this over here. They're showing you why it becomes tangent. You take t0 plus h as h goes to 0. So as h tends to 0, this gets closer and closer until you get the tangent line. And so that was a tangent vector. The tangent line, well, we know how to construct lines. If we have a vector, we can create a line out of it. So here would be your line, and it would be a tangent line. And the equation of this line, so this would be r of t. Sorry, let's call it h of t. Why not? H of t. So now this is our tangent line. That's going to be equal to, so let's call this point over here t0. So it's going to be r of t0. That's your first point, plus t of r prime of t0. And that's going to be your tangent line at that point. So here it is. Okay, L of t. L of t is equal to r of t0 plus t r prime. Did I put in the t? Yeah, perfect. Okay. Good. So, so this needs a calculator. So I guess I'm not going to do it, although it does. Yeah, this needs a calculator. So I'm going to skip this problem. They want us now to find, okay, recall, blah, blah, blah. Sinusoidal is a curve traced out by the point on the rim of a rolling wheel as the center of the wheel moves horizontally. So, okay, look, they're looking at something like this. They have a wheel over here, and as they roll the wheel, they're looking at one fixed point on the wheel. So as they roll the wheel, it goes up, it comes down, hits this, goes up again, comes down. Okay. So now, 1 second. Okay. So now we assume the point begins on the ground and the center of the wheel is moving to the right at speed 1. If the radius of the wheel is 1, then this is traced out by the following curve. So this is what our R of t is. So they already tell us what it is. So they want to find the point where the derivative is horizontal and non-zero. So yeah, that would be all of these points up here. So they're horizontal and they're not 0. And they want to find all the places where this is 0, which my guess would be over here. It would be 0 because it stops moving for a second. Okay, so solution. So first, r prime of t is going, yeah, what's the question?
At those points like 2 pi and 4 pi, wouldn't it be undefined if you took the derivative since it's like a short point?
Yeah, the derivative would be undefined. That is correct. Okay. But I think it would like approach 0 and then become undefined for a point and then.
Oh, okay, thank you.
Yeah, so r prime of t is going to be equal to 1 minus cosine of t, and then 1 plus, sorry, that one disappears. Okay, plus sine of t. Okay. So, so this is going to be 0. So we set this equal to 0, then we are going to need 1 minus cosine of t to be equal to 0 and sine of t to be equal to 0. And so, okay, sine of t is equal to 0 at 0, pi, 2 pi, okay, and so on. Okay, so sorry, we actually do not need cosine to be 0. Okay, let me, if we're only looking for the horizontal, if we're looking for horizontal lines, then we only need the sine of t to be 0. So that would be sine of t is equal to 0, so that would be 0, pi, 2 pi, and so on. So for all of these points, and it makes sense, you can look at the picture and see that that at least for these vectors, you have either a 0 vector or a non-zero vector that's horizontal. So let's say for 0, if you plug that in, you're going to have 1 minus 1 and 0, so that's equal to 0, 0. So that's the 0 vector. So 0 doesn't really count. For pi, you're going to have 1 minus cosine of pi. Okay, so now this is over here is going to be 2. So you're going to have 2, 0. So this works. And then for the next one, so yeah, I assume that the points that are going to work are going to be pi and 3 pi and so on. And the other points, we're going to have 0. So actually, yeah, at these points, there are derivatives. And the reason is because that we are moving in a certain speed to that point. So we are moving to this point. And you can even look over here. You can see that the derivative is not going to be undefined at these points. It's defined. You move in and then you move out. So it's at a certain speed. So it actually is defined because we're inside of the curve. The derivative at the curve would not be defined, but inside it is, and at this point it would be 0. So for example, at 0, 0, the derivative is 0 and 0, so we have the 0 vector. And the same thing would happen, for example, at 2 pi and 0, 4 pi and 0. So here, every time there's a point, you're going to get 0. Again, any questions about this? So, okay, so I think they're going to actually explain what I just said over here. So let's read it quickly. So this shape has a point called the cusps at point 0, 2 pi, 4 pi. If we present this thing as a graph of a function y, then the derivative does not exist at these points. By contrast, the vector derivatives at this thing exist for all t, but the derivative will be 0 at the cusps. So yeah, like I mentioned, and again, the reason is if you think of this thing as a curve, then over here it will not have a derivative. But if you think of it as a path, you're inside of that path. So you're walking along the path at a certain speed, and the t, this thing tells you where you are along the path, and then you slow down to 0, and then you start moving again. So the derivative is going to be 0. Okay. Any questions about that? Okay, so now they ask another question. So they want us to prove that if r of t and r prime of t are non-zero and r of t has constant length, which a good example for this would be a circle. Okay. Then r of t is orthogonal to r prime of t. So let's just see that this makes sense. So let's imagine that r of t is equal to cosine of t and sine of t. So now we have this circle. Then r prime of t is going to be negative sine of t, cosine of t. Now if we dot them, r of t dotted with r prime of t, this is going to be cosine of t minus sine of t plus sine of t cosine of t, which is equal to 0. So the dot product is 0, so that tells us that r of t is, in this case, orthogonal to r prime of t. Again, we satisfied the conditions. The length over here is always constant. It's always 1. Okay, so now let's look at how they go about doing this, solving this problem. So if you look at the derivative of r of t squared, so this is going to be equal to 0 because we just said that the length is 0. So the change in length is going to be 0. Okay, it's also equal to the dot product because we saw that the magnitude squared is equal to the dot product. Then you take the derivative. Each one of these things comes out individually, so you get 2 of them. Okay, so it follows that this thing is equal to 0, so that tells you that they're orthogonal. Any questions about this proof? Okay. Okay, so I think we should stop here. I'm going to continue with integration next time. Are there any questions about what we've done so far? Anything? No? Okay, so I'm going to try to post these recordings this weekend. And I'm going to try to add a link from Joe's recordings. And once again, if you have any questions, just send me an email. Okay?
Can I ask a quick question about the exam?
Yeah.
Is there like any rough estimate on like when those would be graded by chance?
Oh, I finished grading them. Are you guys not able to see the grade?
I didn't see it, but like maybe I just wasn't looking in the right place.
Okay.
I haven't seen mine either.
I haven't seen it either.
Yeah, mine looks like it's still muted.
Okay, fine. So I'm going to try to make sure that those grades get posted. The tests are finished. They have been graded. I just need to post them, I guess. Okay.
Thanks.
Any other questions? Okay. See you next week.